The title of this presentation is Poisson Structure for Triangular Ice. So to begin with a recap from previous presentations, we introduced research areas within statistical mechanics, which are related to some previous works on crossing probabilities in Russell-Seymour-Welch, the localization of the height function for vertex models, as well as integrability conditions and further developing on notions of integrability with computations with the Poisson bracket with the quantum inverse scattering method, which was originally applied in seminal work for Hamiltonian methods and Hamiltonian systems. And more recently in the series, in the last presentation, we introduced algebraic notions from integer valued and set valued tableau for lasso and double Grothendieck polynomials. And we had discussed solutions to the Young-Baxter equation from the colored R matrix. So I wanted to just begin this presentation of the series by giving a brief recap and exhibiting how some different properties of the colored R matrix come into play and how these matrices satisfy Young-Baxter equation, and then exhibit some types of arguments and properties that can be used from the universal R matrix, which also satisfies the Young-Baxter equation, to further develop upon notions of Poisson structure for the three-dimensional six-vertex model, which we'll define and further discuss. So in the previous presentation, we talked about how one can define a double Grothendieck polynomial for set value tableau from integer value tableau, with the difference that the integer value tableau have numbers in each one of the boxes, whereas in the set value tableau, the individual boxes which are given from the semi-standard Young tableau can be populated with sets according to some hierarchy and some ordering of the elements that we contain in the set. And this is given by the fact that one can have an expression for, as we've reproduced here from the Shrimshaw and Buchimas reference in the previous presentation, the factorial Grothendieck polynomial, which is given by summation over T in set value tableau of shape lambda, where we take this beta parameter, which is, as we had reiterated in previous presentations, not to be confused with the inverse temperature of certain models of statistical mechanics that we'd even mentioned and discussed and motivated in even the first presentation of this series that were interesting for us. But the double nature of the Grothendieck polynomials and the Lasso polynomials comes up from the fact that we're taking a direct product of, a direct sum of these two variables and taking a product over either A in the set value tableau as well as a little I in the set value tableau shape lambda. And from the double Grothendieck polynomial that was presented in the previous slide, we can also define a flagged factorial double Grothendieck polynomial, which is given by the fact that we can change the set value tableau of lambda to also be a flagged variety. And imposing these different conditions on the flagging on the set value tableau shape lambda can yield a very similar type of expression for the flag factorial Grothendieck polynomial, given the fact that this T, which also appears in the same exact form that we're using to raise this parameter beta to, is a set value tableau, which has flagging but is still of shape lambda. And the K-theoretic difference operator comes into play in that we can make use of this K-theoretic difference operator that's applied to some little function f, which is given by the scripted d of I term. And it acts recursively because it helps us define recursively double Grothendieck polynomials from embedding words in the symmetric group within each other. For example, we can embed all the permutations on a word of length n plus 1 in the symmetric group within a word of length n, and continue this hierarchy to define a family of recursive double Grothendieck polynomials that are related to each other recursively. And so now I wanted to provide an overview of the third presentation, which is going to still make use of some algebraic properties that we've been talking about in the background, but also further developing and adding on more detail to some presentations earlier in the series, because there were some things that I've mentioned just in more of a general perspective that we can further build upon, namely, what are other types of characteristics of applying a quantum inverse scattering type argument in 3 dimensions for triangular ice. And on top of this, what are more the concrete differences that we see and how these computations with the Poisson bracket are affected and what kind of properties or favorable conclusions will we like of these objects that are analogous to the integrability of the inhomogeneous Hamiltonian flow in 2 dimensions. So we're going to discuss more details of the 3-dimensional quantum inverse scattering type approach. And to do this, we're going to add on to general descriptions like we had mentioned that were from earlier parts of the series. And we're now going to provide information to address the following questions for making connections between the 2-dimensional and 3-dimensional approaches so that we can further discuss some of the algebraic notions that we mentioned earlier in the series. So it's to say that even though we're starting more from an integrability perspective and looking at some other areas of discrete probability, we can further these connections and try to ask and frame and formulate some more algebraic type questions or connections later on in this series once we have these kinds of notions of 3-dimensional Poisson structure or for the 3-dimensional 6-vertex model and triangular ice. So these are all equivalent types of models because we're defining the 6-vertex model on the triangular lattice, and they're in the reference that we're also going to provide the view, draw the viewer's attention to by DiFrancesco on the Arctic curve and several other types of related references. There are many connections that people have already looked at for trying to establish some type of connection between some copy of 3 independent 6-vertex models and relating this triangular ice, and so on and so forth. So there are many different types of ways to relate different models, even if one model is higher dimensional or the other model is lower dimensional. And this is very much going to be looking at a different type of connection from the integrability perspective with the algebraic notions in mind. So we'll want to answer the types of questions which are related to the fact that, as given in the first bullet point, how many terms appear from entries of the transfer matrix that one must approximate with the Poisson bracket. So we're going to be able to provide characteristics and overviews of the system of relations from the Poisson bracket of the entries of the 3-dimensional transfer matrix and draw a connection of the viewers to the computations with the Poisson bracket from the 2-dimensional transfer matrix. And from this type of information, we can think about, with our algebraic notions, also characteristics of the 3-dimensional quantum monodromy matrix. So it's demonstrating and how we can further build upon in this part of the series, in this presentation of the series, how we can look at how the higher dimensional state space of the 6-vertex model to triangular ice in comparison to the state space, the lower dimensional state space for square ice, it provides a lot more algebraic connections that we can really capitalize upon. And so we're also going to think about how is a 3-dimensional transfer matrix defined. So we're going to provide some types of expressions that we would like to take the weak infinite volume limit of. And we're going to look at smaller, lower, well, it's still going to be of the same dimension, but, lower order terms of the approximation for the weak infinite volume limit of the 3-dimensional transfer matrix, and how that very much parts of that methodology and parts of that perspective and school of thought carry over from the 2-dimensional case. And so, as given in the third bullet point, relatedly, how is the 3-dimensional quantum monodromy matrix defined, or what are its types of characteristics? We'll also be able to provide the direct the focus of the viewer to some of these characteristics. And finally, in the fourth bullet point, how do the computations with the L operator expressed in the Pauli basis from the 2-dimensional setting transfer to L operators in the 3-dimensional setting? So we're going to be able to provide some general parallels, but obviously both of these 2-dimensional and 3-dimensional cases won't be exactly the same, but some parts of it will be similar, from which we can form some conclusions and observations then about the parts of the quantum inverse scattering type method that are different. And so additionally, we further describe how algebraic connections from the 3-dimensional L operator along the lines of those mentioned in the previous parts of the series relate to staggering and inhomogeneities in the vertex models. So we're going to also be able to look at maybe applying this type of perspective to a class of vertex models in which we can look at notions of how to colorize integrability or impose inhomogeneities on integrability conditions for triangular ice. So, as we've been saying, besides the dependence of the 6-vertex model on flat and slope boundary conditions like we had discussed and alluded to many characteristics of these types of arguments for Russo, Seymour Walsh, and other parts of the presentations, along with more algebraic focused characteristics of the six-vertex model presented in the previous video, the six-vertex model, and even the triangular ice model for three-dimensional six-vertex model can also be studied from the exactly solvable integrable perspective. So we're still going to want to be able to build onto these characteristics and notions that we've been discussing in a couple of presentations across the series, but we're going to provide a lot more detail in this part of the presentation, and in particular, directly enumerate the set of relations from the Poisson bracket and describe where do these differences in the Poisson brackets emerge and arise, and what type of information and what types of consequences does this have for the three-dimensional quantum monodomain matrix. And so these two references are related in the fact that even in the two-dimensional, and also we'll see in the three-dimensional case, we'll be able, in the two-dimensional case, there are some Hamiltonian flows defined, as well as showing the fact that, showing the conclusion that integrability conditions hold, which can be shown from computations with the Poisson bracket with entries of the transfer matrix. And this method, although it's originally applied in the two-dimensional case, it leaves open many possibilities for applying QISM type approaches in other settings. And as we have been mentioning over the past couple, like one or two presentations in the series, we've been drawing on more of a different class of type of references to prepare ourselves and to prime, to prime the discussion for the triangular ice case. And this is given by the fact that, we mentioned several different types of references that are related to the beta ansatz and inverse scattering type approaches, how from seminal work from Vadiv in other work, rather than the Hamiltonian method paper that we mentioned several times earlier in the series in other presentations. There's even other references for algebraic beta ansatz and how that can be applied for integrable models, as well as there's even connections with Riemann theta function, as well as periodic soliton cellular automaton. So there are many different types of models, and it's very interesting from a mathematical physics perspective to determine what are the different types of intrinsic dependencies that these models have, either on staggering and homogeneities, as well as the ambient state space that one is sampling configurations from with the probability measure. And like we had mentioned, this is relating to the fact that from the D2-3 spin chain, we can make a connection to the inhomogeneous six-vertex model, because we can define a transfer matrix for this higher ring spin chain, like we had mentioned, just like how we can define a transfer matrix for the lower ring spin chain, the D2-2 spin chain. But it's given by the fact that this type of expression is a lot more simpler, because usually how we have to apply a QISM type approach for the two-dimensional and homogeneous six-vertex model, and also for the three-dimensional triangular ice on the triangular lattice for the six-vertex model, is given by the fact that we have to take a trace of a product of L operators. So we have to obtain some type of recursive formula for the L operators by multiplying several L operators together repeatedly, which we can then use to parameterize the system with the Poisson bracket. And this is to say that the universal R matrix and even other types of R matrices, depending upon whether you impose representation theoretic assumptions or more simple assumptions, such as the one given in this slide, in which you can just introduce two external fields to parameterize weights of the six-vertex model and populate the non-zero entries of this 4x4 matrix. It's still related to the fact in one way or another that these R matrices, or the universal R matrix, would either satisfy Young-Baxter equation or some other type of generalization, like many people in the field have looked at the tetrahedron equation as a generalization of this equation, as well as the fact that there are many other different types of formulations and expressions for the eigenvalues of solutions from the Young-Baxter equation, as well as related characteristics. And so to impose additional assumptions on the R matrices, such as the one below for the two-dimensional and homogeneous six-vertex model, the universal R matrix acts as a substitute, and it still satisfies the Young-Baxter equation, but it's given instead of a more simple 4x4 matrix representation that's given by the two-dimensional and homogeneous six-vertex model. We define it in terms of a product, like we had mentioned, of Q exponentials and other combinatorial terms for a total of 4 terms in the factorization of the universal R matrix. And so to begin describing the three-dimensional setting in words, the primary differences and the computations with the Poisson bracket and steps preceding computations with the Poisson bracket include computations for obtaining a set of explicit relations for the entries of the transfer matrix involve much more complicated sets of expressions for products of terms obtained when multiplying L operators together, as well as the fact that, as said in the second bullet point, instead of the Poisson bracket having a set of 16 relations from the two-dimensional L operator, the Poisson bracket in three-dimensional case has a set of 81 relations. So there are many more relations that are involved in the three-dimensional case in comparison to the two-dimensional case. And we can further study as a starting point, just very briefly, we'll rehash some of those characteristics of the two-dimensional case that we had mentioned in the earlier presentation, but we're also at the same time, we're going to be able to put ourselves in a position to describe some other types of characteristics of this three-dimensional system in much more detail rather than sweeping some differences under the rug, which account for the fact that there are 81 relations from the Poisson bracket instead of 16 relations. And even though there's a very big difference in the total number of relations from the Poisson bracket in the three-dimensional case in comparison to the two-dimensional case, at the same time, we can still take away some general ideas and themes, namely the fact that if we want to analyze with some QISM type approach, no matter how high dimensional the matrix is that we're looking at for either the R matrix or other types of dimensionality of the vertex model that we're looking at, it can still degenerate and still be related to expressing some countably many terms that we're going to have to approximate with computations from the Poisson bracket. And that part of the approach is still similar because we can still use bilinearity, Leibniz's rule, or anti-commutativity, as well as potentially the last property, which had connections with some types of properties of metrics in Riemannian geometry with the Levi-Civita connection, like we had mentioned, and that we can still, it's comforting to know that we can still at least use that part of the approach when approximating the Poisson brackets in the asymptotic limit of the quantum monodromy matrix. But however, before we can further study three-dimensional action angle variables for determining whether any type of integrability condition holds or a weakening of an integrability condition, we must discuss the types of relations obtained from multiplying L operators together. And obviously, even if we spend a couple hours on this part of the presentation of this series, I wouldn't be able to still communicate all parts of the computations, but I can just give a couple of features of the computations which appear for the lower order terms and how the viewer can convince themselves about how you would continue these types of computations from the products to L operators, and how eventually with quite a bit of work or a lot of work, you can obtain some asymptotic expansion for, or some pretty exact expansion for the entries of the three-dimensional transfer matrix, and how through computations with the Poisson bracket, how that sheds some light into characteristics properties of the three-dimensional quantum monodromy matrix. And so as a reassuring observation, when comparing quantum inverse scattering types approaches in 2 and 3 dimensions, the approaches in each dimensions are related by obtaining expressions for the entries of the transfer matrix by multiplying L operators together. So that's just another general takeaway, which also holds true, that we can still make use of despite the fact that there are many differences arising in the three-dimensional case. And so in previous parts of the series, we discussed from several perspectives L operators of the type below that hold up to Dynkin automorphism. And we have been describing how this C function is a mapping into a unital associative algebra that's complex valued, as well as the fact that these D1 and D2 terms arise from taking either the tensor product of a differential operator with the identity operator, either from the left or from the right. So we're going to introduce some type of reformulation of this type of expression so that as it's demonstrated in some figures from the preprint that's going to show up on the archive, how we can look at different ways to account for spectral parameters, staggering and inhomogeneities of the vertex models through some reformulation and reindexing of all the terms which appear in this L operator, which hold up to Dink and automorphism. And furthermore, how then this can allow us to replicate, or, not really replicate, but, reflect upon in a similar way some types of products of L operators which have different spectral parameters in the L operator that was given in the two-dimensional case from Colombo and Franco, which was expressed in terms of the Pauli bases sigma plus and minus, as well as sigma z. So to further study other properties of such L operators, we introduce a change of notation for studying the large N limit of the three-dimensional transfer matrix, which will be used of studying the asymptotic limit for entries of the three-dimensional quantum monodromy matrix, so as in the two-dimensional case. And that's to say is that we have the 16 relations that are given on the left-hand part of the slide for the two-dimensional L operator and the two-dimensional quantum monodromy matrix. And this is to say that it's just as an observation, it's important for us to realize that in 2 dimensions, the number of Poisson brackets must be approximated depends only on 4 entries A, B, C, and D appearing in the expression obtained for multiplying the transfer matrix from multiplying L operators together repeatedly. So we can think about, if we're going to look at the three-dimensional transfer matrix, we would have commonality in the set of relations of the Poisson bracket in the two-dimensional and three-dimensional case, because we would still have these 16 relations, but then we would expect many other types of relations to enter into the system if we're going to go from 16 relations in 2 dimensions to 81 relations that we've been mentioning as the number that we're going to define and further describe in the 3-dimensional case. So the 2-dimensional case and the 3-dimensional case, they're obviously going to have some overlap in maybe some of the entries of the Poisson bracket. They can look like they take very similar forms, but in the 3-dimensional case, there's going to appear many other terms with the Poisson bracket that we'll have to approximate, and that we can first begin to list out and further describe in this presentation for describing some type of asymptotic approximations of these Poisson brackets in the next presentation of this series. And this is to say that in 2 dimensions, the expansion of the 2-dimensional transfer matrix in the large N limit was obtained as some product from L operators. So this was a notation that established for demonstrating that the inhomogeneous Hamiltonian flow for the 6-vertex model is integrable, in which you can look at some product of these 2x2 matrices, as well as, from the 2x2 matrices of the L operator, and we indicate I in each one of the entries because we're saying that we're going to multiply however many L operators together and take big N to infinity, so that eventually this product of the terms that we're using to approximate the transfer matrix from the product of L operators, it's going to have infinitely many terms and converge to the weak infinite volume limit of the 3-dimensional transfer matrix. And then this is just related to the system of the 16 relations with the Poisson bracket, because these 16 relations in the lower 2-dimensional case, they allow us to make some conclusions about the asymptotic expansion of the quantum monodromy matrix. And as we've given here, this is exhibiting the reformulation of the 3x3 dimensional L operator that I just wanted to include on the slide, that we're going to further describe and get more into later in this presentation of the series, in which we're going to look to introduce some reindexing of all of the terms, namely the reindexing of the complex valued mapping into the unital associative algebra, as well as the differential operators that we're that we're taking the Q power to, or that appear in the power of the Q parameter, because we're going to be able to look at different ways to take an infinite volume limit for triangular ice by appending different combinations in different spectral parameters and staggering in homogeneities at every position of the site of the lattice of the triangular lattice that we're trying to study the interactions and large volume asymptotic behaviors of this property of the triangular ice model on. So this is demonstrating how we can very much adapt this family of L operators which hold up to Dynkin automorphism and make use of some information from computations with the L operators and products of L operators, and obtaining some recursive type system for this expression of the 3-dimensional L operators, and up to Dynkin automorphism, in comparison to the two-dimensional case, the three-dimensional case for triangular ice, it has some richer, more complicated and intricate interpretations that we have been talking about, whether it be relating to geometric, representation theoretic, combinatorial, as well as interactions between these fields within integrable probability that are more noticeable and more prominent in more complicated in the three-dimensional case than in the two-dimensional case. And so the expansion of the two-dimensional transfer matrix in the large N limit from this product at L operators is related to the fact that we can obtain some type of recursive system, which is dependent upon a sine of 2 eta term, which appears in the expression for the L operator, as well as the fact that we have other recursive terms which they're defined in the paper. And they're dependent upon the staggering and the inhomogeneities of the two-dimensional inhomogeneous six-vertex model. So we can actually now define triangular ice because we had been referring to it several times at different presentations in the series now to just set ourselves formally within this three-dimensional triangular lattice, triangular ice framework. And this is given by the fact that when we define a vertex model, like how we define the six-vertex model, we need to take some products of weights and use this to define a probability measure that we're normalizing by the partition function over the partition function supported over whatever infinite volume we're studying the model on, whether it be the torus, strips of the square lattice, or the cylinder. And so this is given by the fact that for defining triangular ice, in this case, we have 20 possible configurations. So really the triangular ice model or the three-dimensional six-vertex model or the six-dimensional six-vertex model on the triangular model or the triangular lattice is equivalent to the 20-vertex model because we have 20 possible configurations, as well as the fact that we still have 6 weights which are given in this triangular ice model, but it's different from the lower dimensional, two-dimensional six-vertex model, which we had studied earlier, because we group configurations in pairs of 2. So there are 10 configurations on the top and 10 configurations on the bottom. And if we look at the different configurations in the top and bottom rows, we can see that for the W naught weight, which is given by A1, A2, and A3, we have different types of configurations from the 20 vertex model that are related to each other, because as demonstrated in this reference that's reproduced from DiFrancesco's paper that I'm going to include in the bio for a reference, one can look at different types of complementary ways to define different configurations in the six-vertex model, which are grouped together with the same weight, which is given by W naught in the first column. And then even for all of the remaining 18 configurations, which are in the columns omega 1 to omega 6 for the 5 other weights of the 20 vertex model, we have different types of arrangements of line configurations, which we can then take the weight of by taking the product according to the expressions in terms of A1, A2, A3, B1, B2, B3, C1, C2, C3, or even in omega naught, A1, B2, B3 plus C1, C2, C3. And diagrammatically, with the arrows, as we had introduced in the six-vertex model from another paper, or from another figure from DiFrancesco's paper on the Arctic curve of the three-dimensional six-vertex model, we can also define arrow configurations or line configurations, and is given by the fact that each one of these configurations, as we have mentioned in the previous slide for defining the weights for the configurations, it can be defined in terms of 10 configurations in each one of the rows for the 20 vertex model. 10 plus 10 is 20. And then we have different types of visual representations for the line configurations. And in comparison to the two-dimensional six-vertex model for square ice, the three-dimensional six-vertex model, or for the triangular lattice for triangular ice, the 20-vertex model, it's a little bit different because there can exist different combinations of arrows that can simultaneously point inwards and outwards from the configurations. As we can see in the bottommost left-hand corner of the sample space from the line configurations, there are actually no arrows which are pointing directly inside the vertex, because this one line, the directionality of the arrow goes out, it exits this way, as well as the fact that the other arrow, which is oriented on the triangular lattice, it exits this way, as well as finally the last remaining degree of freedom in the triangular lattice exits this way. So it's very much important because it helps us determine for the 20 vertex model how one would color different edges of the triangular lattice depending upon the directionality and the orientation of the arrows about every vertex of the triangular lattice. Okay, so to further describe where additional components with the Poisson bracket arise, we introduced the following representations of the three-dimensional transfer matrix. So we're going to lighten the notation a bit just for this part of the presentation, but it's a little bit more technical, but not much in the actual preprint, because we actually are just going to assume that the two spectral parameters which we need to use to define the three-dimensional transfer matrix and the three-dimensional quantum monodromy matrix is just given by a homogenization of these two spectral parameters to just a single spectral parameter lambda, as well as the fact that we also need to introduce other spectral parameters for the VI and UJ term. And the large N limit of the three-dimensional transfer matrix is given by the fact that we want to look at some transfer matrix of size big M and little n, as well as, which is dependent upon, as we had mentioned, this homogenization parameter, as well as the positions, as well as any other staggering or other influences from the parameters v sub I and u sub j for other positions of the triangular lattice that we're looking at configurations over. And again, this is relating to the set of 16 relations in the two-dimensional case, because we're going to establish some similarities in how the lower dimensional approach for the QISM type methods, it can be extended to obtain a set of 81 relations for triangular ice. And so from the three-dimensional large and limit that we described in the previous slide, the entries of the transfer matrix, we can, when forming the system of Poisson brackets, the entries of the transfer matrix takes the following form. So we have this large N limit of bold-faced of T, which we're just going to adopt a shorthand notation for this presentation of the series as the three-dimensional large N limit of the transfer matrix, and we want to study this asymptotic limit, and then be able to tie this to asymptotic properties of the quantum monodromy matrix in 3 dimensions. And it's given by the fact that we want to establish, as we did in the two-dimensional case, some type of expression for the excuse me, for the three-dimensional transfer matrix, which is given by ABC, DEF, GHU, or sorry, GHI, where each one of these parts of the three-dimensional transfer matrix that we're obtaining from the product of L operators is a function of the parameter U. And I just wanted to begin our discussion of the three-dimensional system of Poisson brackets that we obtained from this three-dimensional transfer matrix, and trying to recursively and asymptotically approximate the entries of this three-dimensional transfer matrix by looking at the CU entry, which is the third entry in the first column. And we can obtain the entries of the Poisson bracket by taking the entries that we have to approximate the Poisson bracket of by taking another three-dimensional transfer matrix, and instead having functions having all these components of the three-dimensional transfer matrix be dependent upon U prime, just another spatial parameter instead of U. And we can form every one of the Poisson brackets that we'd like to approximate in the large N limit from these product of L operators by taking C of U and taking the Poisson bracket with A of U prime, as well as the Poisson bracket of C of U with B of U prime, C of U with C of U prime, as well as C of U with D of U prime, and also C of U with E of U prime. And then also for the 24th relation, we have C of U with F of U prime. And finally, for the remaining, we also have, for the remaining column, we have 3 additional Poisson brackets, which appear in relations 25, 26, and 27 with G of U prime, H of U prime, and I of U prime. So this is demonstrating where the larger number of relations that appear from the Poisson bracket is just obtained by taking 2 approximations for that we're going to that we want to obtain explicit expressions of the three-dimensional transfer matrix, and looking at one three-dimensional transfer matrix, we're going to have all the blocks be dependent upon U. And then in another three-dimensional transfer matrix, we're going to have all of the entries be dependent upon U prime. And we can form different Poisson brackets for that constitute this set of 81 relations by taking pairs of different entries of the U and U prime three-dimensional transfer matrices and pairing them together as arguments in the Poisson bracket. So this is a little bit of an extension just of the two-dimensional case, because it's going to result in several more computations, not only to obtain some type of recursive approximation for the entries of the three-dimensional transfer matrix by multiplying these three-dimensional L operators repeatedly against one another, but also the fact that we need to have more computations for approximating entries of the transfer matrix, and that'll also just translate to more computations for studying the large and asymptotic limit of the quantum monodromy matrix. And so more generally, for all the entries of the three-dimensional transfer matrix, as we had alluded to in the previous presentation, components of the set of the 81 relations can be formed by making generalizations from two dimensions. So we have this generic type of representation for the three-dimensional transfer matrix. And from the three-dimensional transfer matrix, like we had mentioned on the last slide, we can look at relations from the set of 81 relations 19 through 27, which involve as the first argument in the Poisson bracket C of U from this entry, which appears in the first column the first row of the three-dimensional transfer matrix, and how we can extrapolate that to all remaining entries of the three-dimensional transfer matrix for with entries of the U prime three-dimensional transfer matrix to obtain, as we show here, relations 10 through 18, which involve B of U as the first argument in the Poisson bracket, and as in the case with the relation 21, which appeared between C of U and C of U prime as the two respective arguments on the Poisson bracket. In this set of relations for the B of U entry of the three-dimensional transfer matrix, we also have another relation which is given by number 11, which is between B of U and B of U prime. So in every entry of the transfer matrix, there's going to appear at least one relation from the Poisson bracket that's a type of self-interaction term, which is given by the fact that we're going to have a U and a U prime term of the same block or the same component, whether it be ABC, DEF, or GHI. And then even earlier up in the list for the entries of the 81 relations with the Poisson bracket that's given in the three-dimensional transfer matrix, we have the A of U term appearing first, and we have this self-interaction type term appearing between A of U and A of U prime. It appears as the first relation from the first Poisson bracket right out of the bat from the 81 relations that we have with the Poisson bracket, as well as the other remaining entries with the A of U entry as the first argument in the Poisson bracket held fixed, as well as the fact that we're cycling through B, C, D, E, F, G, H, I from the U prime three-dimensional transfer matrix for the remaining other entry in the Poisson bracket. So this demonstrates it makes it pretty clear that the viewer can convince himself that even if we have a higher dimensional transfer matrix, and then the conditions for studying in the computations that we would like to approximate with the Poisson bracket for studying the large and asymptotic limit of the quantum monodromy matrix, it's ultimately going to degenerate to some countably many computations with the Poisson bracket from the entries of whatever L operator product of L operators that we're looking at. So this is exposing and adding on some further detail on this set of 81 relations. And as we had mentioned in the previous presentations, rather than just mentioning that the three-dimensional case is a lot more complicated and has more relations than the two-dimensional case, which can be a pretty vague, if not very vague statement, we can provide a concrete difference to the difference and in how we increase the state space of the triangular ice by one dimension to go to the three-dimensional 20 vertex model from the two-dimensional inhomogeneous six-vertex model, and what is the change in the total number of computations with the Poisson bracket that we encounter, which would still help us study some type of three-dimensional action angle coordinates. And so we can begin by examining the set of relations from the Poisson bracket in 3 dimensions by observing the following. So now we're going to actually get to the expression for the 3-dimensional L operator. And how I mentioned, we're going to reindex or reformulate this type of quantity so that we can establish and study the influence as well as potentially the dominant forces, either through staggering or inhomogeneities, or looking at different weights of configurations for triangular ice, as we're adding in different vertices, either in 1 degree of freedom that's given in the triangular lattice, as well as the fact that we can also take the large N limit or the asymptotic limit in another degree of freedom and be able to piece this local type of information together for some asymptotic global picture for some large N limits of the transfer matrix in the quantum monodromy matrices in 3 dimensions. So this is further developing upon several different parts of the presentations of the series, because we were first looking at the lower 2-dimensional case in the presence of inhomogeneities, but now we're looking at the 3-dimensional case, and we can even impose additional complexity in the 3-dimensional case, because we're going to want to look at whether there's any types of connections with the colored R matrices, or whether there's any way that we can further build upon these notions of integrability by colorizing integrability, which is even related to some open questions, which is going to be listed or going to be described and phrased in the last concluding part of the presentations with challenges and prospects. So there's still many interesting directions. And this is given by the fact that the reformulation of the 3-dimensional L operator is given by the fact that we can look to reformulate the spectral parameters and the staggering and inhomogeneities, which go into play for the complex valued mapping into the unital associative algebra, as well as given by the fact that we would like to just reformulate the differential operators dj of k and dj of k plus 1, just adding 2 indices to this expression in terms of 1, because we're going to look at still the tensor product of the differential operator from the construction of the universal R matrix over the tensor product of 2 spaces, given the fact that we also want to look at whether the position vector, which we're given as boldface R, it's either equal to some arbitrary position E sub k. So we can take like E sub 1, E sub 2, E sub 3, and we can look at the differential operator obtained that's obtained from looking at enforcing a differential operator about each segment of the triangular lattice that we're taking the infinite volume limit of for the approximation quantifying Poisson brackets for studying the quantum monodromy matrix and the large N asymptotic limit of the transfer matrix, as well as the fact that if we shift this k parameter, which appears as one of the indices in the differential operator d sub j of k, with d sub j of k plus 1, it's given by the tensor product with the differential operator and the identity to the left, as well as given by the fact that we have the indicator that the position vector is equal to ek plus 1. So we're just denoting these basis vectors ek and ek plus 1 as 2 of the degrees of freedom of the triangular lattice, because we would like to study and be able to look at and define differential operators along each component of the finite volume that we're taking, and be able to factor this expression and this perspective into a reformulation of the L operator that we can then use to take products of L operators for different spectral parameters, either in any degree of freedom of the triangular lattice, which is directly paralleling the type of different spectral parameters that we included for the 2-dimensional 6-vertex model. So this is another parallel, at least, that we can carry over, which can help us get our foot in the door first for taking products at L operators and then being able to circle back from this set of 81 relations with the Poisson bracket, and how we can form different types of these relations, and how this set of 81 relations, it very much relates to a more generalized version that would share some characteristics for the set of relations that would hold in 2 dimensions with the Poisson bracket from the entries of the 2-dimensional transfer matrix in the large N limit. And so this is given by the expression in that we can take the expression which appeared in the reference from the exercises with the universal R matrix from several authors, and up to Dink and automorphism in 3 dimensions in comparison to the 2-dimensional case, we can have some action of the Dink and automorphism, which can even help us conclude and infer different types of properties up to the action of this Dink and automorphism from the set of integrability conditions that we didn't have this type of interpretation in the 2-dimensional and homogeneous 6-vertex model. So it's again underscoring how reformulating different types of 3-dimensional properties, it really helps us and helps us get more interpretations and get more connections between several different areas of math at once, which weren't as prominent or as noticeable in the 2-dimensional case for the 6-vertex model and the presence of inhomogeneities. And so taking the weak infinite volume limit to obtain the 3-dimensional transfer matrix that's supported over infinite volume is given by the fact that we would like to take the trace of some product of these L operators where we can vary the K index, which is given in the bottom of each one of the terms, as well as varying the J index. So we can vary these indices, these J and K indices, which we're inserting into the reformulation of the spectral parameters, the inhomogeneities, as well as the differential operators from the construction of the universal R matrix over the tensor product of 2 spaces. And then this can allow us to form some type of interpretation about either which spectral parameters we include as we take the volume in the 3-dimensional or in the triangular lattice of the 20-vertex model to infinity through a weak infinite volume limit. And so for large n approximations of the entries of the quantum monodromy matrix, one must obtain a recursive system from multiplying several dimensional L operators together repeatedly. And we have been mentioning even before this slide and the title of this slide this a couple of times throughout the presentation and establishing concretely more of the types of connections from the 2-dimensional case. And so below, one of the column of the 3-dimensional transfer matrix is obtained when multiplying a few L operators together. So when we're looking maybe for a QISM type approach, because we have to look at products of L operators together, the beginning of the approach, it may seem maybe a little non-intuitive because we just have to kind of perform a brute force type of approach and perform these brute force types of computations a couple of times to obtain the desired recursive system, which we can then substitute into the parameterization of the entries of the set of 81 relations from the 3-dimensional case for the 3-dimensional asymptotic quantum monodromy matrix. And this is given by the fact that, as we'll underscore further in the next presentation when we're recapping the material from this presentation in a couple of the highlights, we very much have to form a type of dictionary between the staggering, the inhomogeneities, and the tensor in the differential operators, which are inherent in which they go back to the universal construction of the R matrix, because we have several different types of terms, whether it be a QD31 term corresponding to the differential operator at J is equal to 3 and K is equal to 1, as well as several other expressions which can occur when we're repeatedly multiplying L operators together. So we can even have, as given in the second column of this column of the of some finite volume approximation to the large n limit of the 3-dimensional transfer matrix, an A3 of 1 dagger term, as well as Q raised to this differential operator, as well as another psi 3 of 1 term, which is responsible for a complex value parameter that's mapping into the unital associative algebra. So it's just to say that these types of computations, they can get pretty complicated quite quickly because we have to keep track of different types of influences, whether it be spectral parameters, inhomogeneities, or staggering, that can come into the way, or that can come to influence different terms in the product of L operators. But besides expressions in the first column from a product of L operators that we had given on the previous slide, which has several different types of contributions, there exists a similar set of expressions that can even be more complicated. And a lot of these types of complexities in the computations from the products of L operators, some of them do appear in different types of forms in the 2-dimensional case, because the entry of the quantum monodromy matrix, or the transfer matrix, and the quantum monodromy matrix in 3 dimensions, the expressions are much more complicated when we have to end up multiplying certain interaction terms together, like a q to the -2 minus another term, which then complicates the types of computations that we use when multiplying L operators together, because we have to work out explicitly several terms for products between several terms at once, which makes our life in this case a lot more complicated. And in the paper when I provide, or in the preprint when I provide an overview of the expression or of the three-dimensional quantum inverse scattering type approach, I provide another type of expression for this E2 prime term, which is given by the second row in this column of a product of L operators that's used to approximate a finite volume limit of the three-dimensional transfer matrix. And it just also has many features in that we have several products between q raised to some differential operators, as well as complex valued staggering parameters, which we shouldn't be surprised make its way into the asymptotic approximation for the three-dimensional transfer matrix, as well as given by the fact that there are other types of parameters such as q to the -d31 plus d32, as well as several other parameters which appear in the superposition, which are derived in this part of the paper. And furthermore, it's also of interest to obtain entries for the columns of the products of L operators, others of which take the following form, in which we can look to vary the j or k parameter of the product of L operators. And in this case, we can obtain very similar products, whether it be q as given in this first row, q to the d31 plus d34, namely taking q and raising it to a superposition of two differential operators, as well as a q minus term, like we had mentioned, can appear in be responsible for several types of complexities which appear in computations with the Poisson bracket for the 20 vertex model, as well as even A4 of 1 dagger terms. So there can be very much a mixture of all these terms, and it can be a pretty meticulous business to have to look at different types of these products at L operators and carefully track which terms appear and where, and how this influences the large N asymptotic properties of the transfer matrix and quantum monodromy matrix. And in 3 dimensions, an analog of the identities for the tensor product of the Poisson bracket of entries of the large N transfer matrix takes the same form. So as we mentioned, we can define either boldface T, as we had alluded to earlier in the presentation, as the 3-dimensional transfer matrix, and we can take the limit of certain parameters either in the 3-dimensional transfer matrix, either to positive or negative infinity, which we can either denote as boldface T minus or boldface T plus, boldface T minus and boldface T plus, and we can look at different types of expressions for the Poisson bracket, the tensor product of the Poisson bracket between these two portions of entries of the transfer matrix. And as in the 2-dimensional case, it's also reassuring to know that, or to be able to observe and convince ourselves that this identity for the tensor product of the Poisson bracket has an expression, has an equality in that we can look at some 3-dimensional R quantity times T minus the negative limit of the 3-dimensional transfer matrix, which is a tensor product with another copy of the 3-dimensional transfer matrix under different types of spectral parameters. So we can look at making use of these expressions, these types of expressions, for either taking the limit of to positive or negative infinity of the 3-dimensional transfer matrix, and how we can make use of different types of 3-dimensional objects and quantities for writing an expression for the tensor product of the Poisson bracket of two entries of the 3-dimensional transfer matrix. And so with such identities like what we had obtained before, we look to obtain a system akin to this system. And because this was on YouTube, the viewer can pause this part of the presentation to look more at this system of relations, because it's just the types of 16 relations that we have obtained in the 2-dimensional case that we're able to reparameterize from obtaining some type of recursive system for the product of L operators, which allowed us to approximate and study asymptotic properties of the 2-dimensional transfer matrix, And in the three-dimensional case for the transfer matrix and the quantum monodromy matrix, it's very much relating to the same type of thing in that we want to draw from computations of products of three-dimensional operators, and from this family of L operators, which holds up to Dynkin automorphism, to be able to reformulate and reparameterize the set of 81 relations, just like how we did in the set of 16 relations in the two-dimensional case, which would then allow us to make some type of interpretations potentially about integrability or three-dimensional action angle coordinates, which would then demonstrate some type of similar conclusions that can be established for inhomogeneous square ice and triangular ice. And so behind the two identities for the tensor product of the Poisson bracket, this three-dimensional quantity R that we had introduced takes an analogous form to the two-dimensional quantities, in which R plus of 3D is given by the limit of a y tends to positive infinity of some quantity E3D of the three-dimensional six-vertex model. And I'm not going to define these E quantities here, but they're included in the two-dimensional inhomogeneous six-vertex model paper, and they're used because they're expressions which appear in the tensor product of another copy of this E term with slightly different spectral parameters that's multiplied by the three-dimensional R term. So this is to say that we can take the limit as y tends to positive or negative infinity and obtain either R3D plus or R3D minus, which come into play in these expressions that we also expect to hold and know to hold for equalities between the tensor product of the Poisson bracket from entries of the three-dimensional transfer matrix, either as the entries go to positive or negative infinity. And additionally, the three-dimensional R terms and the tensor product of the Poisson bracket on the previous slide, which are given, like we had mentioned, the R3D plus and R3D minus term, which are respectively given by different limits, by the two limits as y tends to positive infinity or y tends to negative infinity, are also used in the following tensor product, in which we have this, like we said, this type of general representation of the three-dimensional transfer matrix, and we're taking R multiplied by the three-dimensional transfer matrix and the tensor product with the generic representation in the generic form for the three-dimensional transfer matrix, and subtracting off the generic representation for the three-dimensional transfer matrix and the tensor product of this with the three-dimensional transfer matrix multiplied by R minus. So R plus and R minus, they have a type of symmetry that comes into play, as we say, in some type of anti-commutativity representation for the two-dimensional computation with the tensor product for the Poisson structure, and then in homogeneous six-vertex model that also carries over for triangular ice. And so ultimately in three dimensions, the existence of action angle coordinates for a three-dimensional Hamiltonian flow would imply that the Poisson bracket of the action angle coordinates from this single inhomogeneous parameter that we project the two inhomogeneities of the triangular ice model to has a zero Poisson bracket with respect to the complex conjugate of the three-dimensional coordinates. And also, this just results from the fact that in the two-dimensional case for the inhomogeneous Hamiltonian flow, the whole conclusion of integrability of the Hamiltonian flow, which results from integrability of the limit shades from solutions to the Euler-Lagrange equation, states that the Poisson bracket of the action angle coordinates with the complex conjugate of the action angle coordinates also vanishes. So we can look to establish some type of similar conclusion, and it's not so bad to think about what these types of properties would be. But as Ray mentioned, the big difference comes from the three-dimensional triangular ice Poisson structure in the set of 81 relations, and how that would bleed into and how that would reflect into other computations that we're going to look to carry out with the Poisson bracket, even though we can still use Leibniz's rule in anti-commutativity and bilinearity, which were the three properties of the Poisson bracket that we use the most prominently for the inhomogeneous six-vertex model in two dimensions. And so in three dimensions, part of the large N asymptotic expansion of the transfer matrix would include the following terms, which is to say that we have this Q D of 1 term, which is appearing in the first, and then we have we take this we can take this little index n that appears in the top to little n, which is corresponding to taking some weak finite volume limit for some to hopefully approximate asymptotically the infinite volume properties of the transfer matrix and the quantum monodromy matrix over the triangular lattice. And then we can have other types of terms which appear in which we vary the k term, like d12, and then we can vary that term, which would then result in another collection of terms up to like as we have in the first entry of the three-dimensional L operator, the Q dn of 2. So this is given some type of non-rigorous or imprecise expression that we can have in mind when we're performing the computations with these L operators that hold up to Dynkin automorphism that would be related to the definition of the three-dimensional transfer matrix. And so hence, with the aforementioned basis elements of the triangular lattice, we can rephrase computations with the Poisson bracket from the set of 81 relations. So like we had said, we took two basis vectors of the triangular lattice and we defined the differential operators d sub j of k and d sub j of k plus 1. And from the general representation or generic representation of the three-dimensional transfer matrix, we can write down some, we can just list for the viewer an idea how they can get an idea of the set of 81 relations from fixing arguments from the first entry of the Poisson bracket from the corresponding entry of the three-dimensional transfer matrix and forming a system of relations of the Poisson bracket. And we can look to make use of the product of L operators so that we can approximate and, or even explicitly define every one of the terms that appear in the Poisson bracket. And then we would very much be in a similar type of situation that we were in the two-dimensional case in the presence of inhomogeneities and being able to perform some countably many number of computations with the Poisson bracket and be able to rearrange terms either using, like we said, bilinearity, Leibniz rule, or anti-commutativity to attain some asymptotic expansion of these entries and being able to tie those computations and that set of relations back to notions of integrability. And so we have been further developing on this perspective, which exhibits clear similarities and on the other hand, many differences with computations with the Poisson bracket in 2 dimensions, like we had mentioned a couple of times in presentations throughout the series, in which we have this L operator, which is expressed in terms of sign functions and the Pauli basis and other Pauli basis elements, and the quantum monodromy matrix, which we express in some 2x2 generic form, and how we can carry that over to the 3-dimensional case, as well as very clearly describing where the differences and difficulties and additional complications for the computations with the Poisson bracket would arise. And so for approximations to the 3-dimensional transfer matrix, like the 3-dimensional transfer matrix that was given in a very similar expression in the previous slide, we can now turn to a system of Poisson brackets to approximate in the large N limit, like how we have mentioned. From the set of 81 relations 1 through 9 were given by holding the first argument of the Poisson bracket fixed, and how we can iterate through all of the other types of generic representations for the entries of the 3-dimensional transfer matrix, and being able to study properties, as a result, corresponding properties of the 3-dimensional quantum monodromy matrix. And so the concluding remarks that we wanted to close out with for this presentation of the series is that we discuss more details on the 3-dimensional quantum inverse scattering type approach. And to add on general descriptions provided in earlier parts of the series, we discuss how many terms appear from entries of the transfer matrix that one must approximate with the Poisson bracket, and how is the 3-dimensional transfer matrix defined. Relatedly, how is the 3-dimensional quantum monodromy matrix defined? And we didn't exactly define it, but we pretty much hinted at several types of properties that would relate to how one would define the quantum monodromy matrix and how it relates to the computations from the 81 Poisson brackets that we can write out by looking at different entries of the generic representation for the large N limit of the asymptotic 3-dimensional transfer matrix. And how do computations with the L operator expressed on the Pauli basis from the two-dimensional setting transfer the L operators in the three-dimensional setting? We drew many different parallels between the two-dimensional case and the three-dimensional case, as well as how it relates to the enforcing of the domain wall boundary conditions and how that relates to the appearance of the Pauli basis in the two-dimensional L operator, which carries over into the expressions for the two-dimensional transfer matrix and the two-dimensional quantum monodromy matrix, as well as their respective asymptotic limits. And finally, as a new contribution to this series in this presentation, we emphasize 81 relations appearing in computations in 3 dimensions with the QISM type approach in comparison to 16 relations appearing in computations with a Poisson bracket in 2 dimensions. And thanks for watching.